the world is aflame. Across the continents, from the sun-scorched deserts of North Africa to the frozen steppes of Russia, the brutal machinery of war grinds relentlessly, devouring men and materiel at an unimaginable pace. For the United States, newly thrust into the global conflict by the attack on Pearl Harbor, the challenge is Herculean: how to swiftly produce the prodigious quantities of weapons, ships, and aircraft needed to fight a war on two vast oceans, against enemies who have had years to prepare and perfect their war machines. The answer, screamed from every propaganda poster, blaring from every factory loudspeaker, and whispered with desperate urgency in the halls of power, is simple: production. More, faster, better, and above all, now. But even as the vast, powerful gears of American industry begin to turn, churning out tanks and planes, ships and bullets, they are grinding against a brutal bottleneck, a seemingly insignificant piece of steel, yet absolutely vital to every weapon that fires a bullet or shell, is holding back the tide. Specifically, the bolt for the M1919 Browning .30 caliber machine gun, a ubiquitous workhorse weapon found mounted on tanks, affixed to the wings and fuselages of aircraft, clutched in the hands of infantrymen, and protecting every jeep, truck, and landing craft. It is the unassuming heart of a weapon that is, at this very moment, indispensable to the American war effort. Imagine the deafening, soul-rattling clamor of a factory floor. The air is thick, almost opaque, with the acrid smell of cutting oil, the metallic tang of hot steel, and the pervasive scent of human sweat. You can feel the ceaseless vibration of massive, hydraulic-powered machines shaking the very ground beneath your feet, a tremor that travels up through your boots and into your bones. But the assembly lines, which should be flowing like powerful, unstoppable rivers of steel, are stuttering. They are halting, backing up, waiting. They are waiting for one small, precisely machined component, the M1919 bolt. This isn't just a simple block of metal, it's a complex, intricately engineered mechanism, requiring a painstaking ritual of milling, grinding, and tempering processes. Each individual bolt demands nearly 27 man-hours to produce, a painstaking ritual of precision that, in the rush of wartime, cannot be rushed without risking catastrophic failure. Every single M1919 machine gun needs one of these bolts. Tanks carry several, often in multiple turrets. Bombers like the B-17 Flying Fortress and B-24 Liberator are bristling with them. A dozen or more bristling from every defensive position, and the demand from the front lines is not for hundreds, not for thousands, but for millions. The skilled machinists, the backbone of America's vaunted industrial might, are working around the clock, their hands perpetually raw and calloused, their faces grim with fatigue and the knowledge of the stakes, but they cannot keep up with the insatiable The backlog is growing exponentially, threatening to choke the supply of these vital weapons, leaving soldiers, sailors, and airmen underarmed, outgunned, and desperately vulnerable in the face of a well-equipped enemy. This single, seemingly minor bottleneck in production is costing lives on distant battlefields, delaying critical offensives, and prolonging the brutal conflict with each passing day. This is the nightmare that hangs like a suffocating shroud over the War Production Board in Washington. This is the crisis that keeps generals awake at night, staring at charts of dwindling supplies and escalating demand. A simple, unassuming piece of steel, demanding too much time, too much precision, threatening to unravel the entire Allied war effort before it can even truly begin. A radical solution is desperately needed. A departure from established manufacturing dogma, a challenge to the very foundation of how weapons are made. But who would dare challenge the orthodoxy of precision machining, especially when lives and the fate of nations hung in the balance? The answer, as it so often is in times of profound crisis, would come from an unexpected place, not from an engineer in a pristine, state-of-the-art laboratory, but from a mad welder on a greasy, cacophonous shop floor, a forgotten man armed with nothing but raw ingenuity, a discarded idea, and an unshakable belief that there had to be a better way. To fully grasp the magnitude and the deeply ingrained nature of the M1919-bolt crisis, one must first understand the reigning dogma of manufacturing, particularly in the sacred realm of weaponry. This dogma was built upon three unshakable tenets: precision, reliability, and interchangeability. These were not mere buzzwords. They were the sacred commandments, born from generations of industrial evolution, and enshrined for very good, very practical reasons. A firearm, particularly one designed for the brutal, unforgiving environment of combat, is a complex machine where every component must fit together with excruciating accuracy to ensure safe, consistent, and dependable operation. A bolt that is even a fraction of an inch off, a surface that is not perfectly smooth, a dimension that is not held to microscopic tolerance could lead to catastrophic jams, dangerous misfires, or even the complete, spectacular failure of the weapon, endangering the soldier who relied on it for his very life. The M1919 Browning machine gun, designed by the legendary John Moses Browning, a man whose name was synonymous with firearm perfection, was, in its own right, a testament to American engineering excellence. It was rugged, dependable, and capable of sustained, punishing fire for hundreds of thousands of rounds, but only if its internal mechanisms, and especially its intricately designed bolt, were manufactured to the most exacting specifications. The bolt itself, though small enough to fit in a man's hand, was a marvel of micromachining. It featured intricate channels for the firing pin, precise locking lugs designed to engage the receiver with absolute certainty, and complex camming surfaces that orchestrated the seamless extraction of spent casings and the chambering of new, live rounds. Every single surface, every single angle, every microscopic dimension was considered critical for the weapon's flawless function. The traditional method of production for such a component involved a series of highly specialized, industrial-scale milling machines. A solid block of high-grade, expensive steel would be slowly, meticulously carved down. Each pass of the cutting tool, a blur of spinning carbide, would remove a minuscule amount of metal, gradually shaping the component with almost surgical precision. Then came the grinding, a process that further refined the surfaces, followed by specialized heat treatment to harden the steel to its required resilience, and finally, more grinding to achieve the final, mirror-smooth finish and micron-level tolerances. This entire process was painstakingly slow, incredibly expensive, and required an army of highly skilled, almost artisanal machinists, a precious and limited resource in wartime. The existing tooling and machinery were already operating at their absolute maximum capacity, 24 hours a day, 7 days a week, and new milling machines simply couldn't be designed, built, and deployed fast enough to meet the insatiable, accelerating demand of a global conflict. The problem, it was understood, wasn't unique to the M1919 bolt. Every weapon, every critical engine part for planes and tanks, every piece of ordnance with complex internal geometry suffered from this same inherent limitation of subtractive manufacturing. You started with a large, expensive block of raw metal, and through a laborious process, removed everything that wasn't the part. A process that generated mountains of expensive scrap metal and consumed untold hours of skilled labor. For complex shapes like a gun bolt, it was, everyone believed, the only way. Any deviation from this established path, any suggestion of a shortcut, any proposal for anything less than absolute, microscopic precision was met with immediate, unyielding resistance. It was seen as heresy. To propose alternatives was to invite scorn, even accusations of endangering the troops by fielding unreliable weapons. The vaunted reputation of American-made weapons, their legendary reliability, was built upon this bedrock of precision manufacturing. To challenge it was to challenge the very foundation of industrial warfare, to question the expertise of generations of engineers. Yet, the war effort was screaming for speed, for volume, for solutions that defied tradition and embraced a new, brutal pragmatism. And one man, an outsider to the rarefied world of high-precision machining, was about to offer an answer that would turn the entire manufacturing paradigm on its head, proving that sometimes necessity truly is the mother of invention, even if that invention appears, at first glance, to be sheer madness. In the vast, sprawling, and ceaselessly churning network of American industry mobilized for total war, there were countless individuals toiling away, their names largely unknown to history, their individual contributions often lost in the sheer scale of the collective effort. One such man was John Garand. No, not that John Garand, the legendary, almost mythical designer of the iconic M1 Garand rifle, a weapon that would famously win the war. This was a different John Garand, a skilled and seasoned welder, a master of his craft, quietly working at the Springfield Armory, the venerable birthplace of American military firearms. This John Garand was not an engineer by title, nor a designer in the traditional sense. He was a man of the shop floor, a master craftsman capable of joining metal with an artistry bordered on alchemy. He understood the properties of steel, the nuances of heat, and the sheer power of fusion. While the machinists around him meticulously carved steel, reducing massive blocks to intricate components, Garand saw things differently. He saw complex, three-dimensional shapes, not as reductions from a solid block, but as dynamic assemblies of simpler, more easily produced components. He understood the inherent power of fusion, of combining disparate pieces through the focused application of intense heat into a strong, unified, and perfectly functional whole. The M1919 bolt, with its intricate geometry and demanding production time, was a constant topic of frustrated conversation on the factory floor. The bottleneck was universally lamented, a source of endless headaches and mounting pressure from the war production board. Garand, listening intently to the machinists, lamenting the 27 agonizing man-hours required for each bolt, began to think, to visualize the problem through the lens of his own craft. He studied the complex geometry, the myriad cuts, the precise angles, and the intricate internal channels that defined the bolt's function. And then, a radical, almost heretical idea sparked in his mind, an idea so unorthodox, so seemingly outlandish, that it was almost certainly destined for immediate ridicule and outright rejection. What if they didn't mill the bolt from a single, expensive, and time-consuming piece of steel? What if, instead, they welded it? The concept, in its essence, was disarmingly simple, yet profoundly revolutionary for the time. Instead of spending countless hours on expensive milling machines, slowly and meticulously carving metal, they could stamp out several simpler, less precise pieces of metal using high-speed presses. These stamped pieces, which required far less skilled labor and vastly reduced machining time, would then be brought together and, with a few precise welds, expertly fused into the final, complex, the shape of the bolt. The amount of subsequent machining required would be drastically reduced to a mere fraction of the original process. The time saved, Garand intuited, would be enormous, potentially revolutionary for the entire war effort. Garand was keenly aware of the inherent challenges his idea presented. Welding, while capable of creating incredibly strong joints, also introduced heat distortion, making it difficult to maintain the microscopic tolerances required for a precision firearm component. The resulting parts would inevitably be looser than a traditionally milled part. Furthermore, the stigma associated with a welded gun part, a symbol of perceived inferiority and corner cutting, would be immense within the engineering community. But he also knew, with a visceral understanding born of the urgency of wartime, the desperate, escalating need for speed and volume. He knew that good enough and fast enough in the hands of 1,000,000 soldiers was infinitely better than perfect but scarce in the hands of 10,000. He was utterly convinced that a sufficiently strong and reliable bolt could be produced using this method, drastically cutting production time and, by extension, saving countless lives. His supervisors, initially, scoffed at the idea, dismissing it out of hand. Welding, they argued, was for structural supports, for rough assemblies, for non-critical components, not for the delicate, high-stress, high-precision internal mechanisms of a machine gun. It was a mad idea, they declared, a desperate measure that would surely compromise the integrity of the weapon and, most unforgivably, endanger the troops. But John Garand persisted. Driven by the urgency of the war, the mounting pressure from the front lines, and the unshakable conviction of his quiet vision, he began to tinker in secret, working on his own time after his shifts. Determined to prove that his rejected gun held the secret to a manufacturing revolution, a trick that could, in one stroke, save 50 million man-hours and decisively contribute to the Allied victory. John Garand's initial attempts to pitch his welded bolt idea to the entrenched establishment at the Springfield Armory, and indeed to the broader military-industrial complex, were met with the predictable and frustrating brick wall of bureaucratic skepticism and deeply ingrained manufacturing tradition. The immediate, almost knee-jerk reactions were uniform. "It's impossible. It'll never hold up. It'll jam the guns." The seasoned engineers, steeped in the rigorous, almost sacred standards of precision machining, found it virtually impossible to fathom a critical component, like a machine gun bolt, being anything but a monolithic, meticulously milled piece of solid steel. Their entire careers, their professional reputations, their very understanding of quality and reliability were built on that bedrock of subtractive manufacturing. The idea of introducing welding, a process often associated with less precise, more structural applications, into such a delicate mechanism, was, to them, an affront to engineering principles. But Garand, despite the dismissals and the polite but firm rejections, was not easily deterred. He possessed a quiet, unwavering persistence, born not of stubbornness, but of a profound understanding of the stakes. He grasped the urgency of the war, the desperate need for rapid production, far better than many of the desk-bound administrators and theoretical engineers. He saw the mounting casualty lists, the desperate calls for more weapons from generals like Patton and Eisenhower, and he knew that tradition, in times of such profound crisis, could be a dangerous, even fatal, luxury. He was a practical man, a hands-on problem solver, and the problem staring him in the face, the agonizingly slow production of a vital component, was plain and undeniable. He was convinced that the current method was simply too slow to win the war. So, when his official proposals were rejected, Garand took matters into his own hands. After his demanding shifts, in the dim, often cold light of his workshop, working in the precious hours of his own time, he began to experiment. He gathered rejected scraps of steel from the factory floor, bits of metal that would otherwise be melted down, and, using simple dies, he began to stamp out crude prototypes of the simpler, more easily manufactured bolt components. Then, patiently, meticulously, and with a craftsman's intuition, he began to weld them together. He experimented with different types of steel alloys, understanding their unique properties under heat. He refined his welding techniques, learning how to manage the intense heat distortion how to ensure sufficient penetration and strength in the welded seams, and how to control the subtle changes in the metal's crystalline structure. It was a lonely, often frustrating, and certainly unsanctioned endeavor, but his unwavering belief in the fundamental soundness of his idea never faltered. He knew that the key wasn't to achieve the exact same level of microscopic precision as a bolt milled from a solid block that was, for a welded part, inherently impossible. The true key was to achieve a sufficient level of reliability and strength, one that would demonstrably stand up to the brutal, violent stresses of combat while drastically reducing the manufacturing time and cost. He wasn't aiming for theoretical perfection. He was aiming for battlefield effectiveness and industrial volume. He was aiming for victory, and he knew that victory demanded speed. After weeks of tireless experimentation, then months of refining his technique, Garand finally produced a prototype that he believed was ready for a proper, official test. It was undeniably rough around the edges, a testament to its improvised, shop floor creation. But it held together with a quiet determination. He presented it again to his supervisors, this time not with a theoretical proposal, but with a tangible, working example in his hands. The sight of a fully functional, welded bolt, still so alien to their sensibilities, was met with a mixture of fascination, professional curiosity, and lingering doubt. But the sheer audacity of his persistence, combined with the increasingly desperate need for any solution to the M1919 bottleneck, finally convinced them to grant him a formal, official test on the Armory's firing range. The fate of his mad idea, and potentially the fate of millions of man-hours and countless weapons, hung precariously in the balance, resting on the performance of a single, welded piece of steel. The day of the formal test arrived, a tense, almost somber affair on the Springfield Armory's secluded firing range. A small, select group of high-ranking engineers, ordnance officers, and War Production Board officials gathered, their faces etched with a mixture of skepticism and grim hope. A standard M1919 Browning .30 caliber machine gun was mounted securely in a firing stand, its heavy, fluted barrel gleaming with a fresh coat of oil. Next to it, a vast pile of ammunition belts lay waiting, hundreds, perhaps thousands, of rounds ready to be fed into the weapon. The official, meticulously milled bolt, the product of countless man-hours and generations of manufacturing dogma, was carefully loaded into the gun. The test began. Thump, 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 thump. The gun barked, spitting out its rounds with its characteristic steady, almost soothing rhythm. Flawless, reliable, the epitome of American manufacturing precision. The standard had been set. Then came the moment of truth, the moment everyone had gathered to witness, and secretly, many expected to see fail. The standard milled bolt was removed, and John Garand's welded prototype, visibly cruder in its finish but functionally identical, was carefully inserted. A profound hush fell over the small group. Skepticism hung heavy in the crisp morning air, thick with the smell of gunpowder. Could this Frankenstein's monster of a bolt cobbled together from stamped pieces and fused with fire, possibly endure the violent, repeated stresses of a machine gun in full automatic fire. The engineers exchanged guarded glances, their professional reputations, in a subtle way, on the line. The order was given. The trigger was squeezed. Thump, 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 thump. The M1919 roared to life again. Smoke, hot and acrid, curled from the barrel. Spent casings, gleaming brass cylinders, flew from the ejection port in a steady stream. The gun ran, and ran, and ran. Belt after belt of ammunition, each containing hundreds of rounds, was fed through the weapon with relentless efficiency. The staccato bark of the machine gun echoed across the range, punctuated only by the clatter of empty links falling to the ground. The welded bolt held, it extracted, fired, and ejected without a single jam, without a single failure, without a hint of stress or malfunction. The rhythm of fire was indistinguishable from the gun using the traditionally milled bolt. The assembled engineers and officials watched their expressions slowly, almost imperceptibly, shifting. Doubt gave way to astonishment. Astonishment turned into a dawning, almost incredulous, realization of the profound implications of what they had just witnessed. This rejected gun, this mad welder's trick, worked. Not just adequately, but reliably. It performed its critical function under the extreme, punishing conditions of sustained automatic fire, cycle after punishing cycle. The internal stresses were immense. The heat generated by the rapid firing was intense, yet the welded joints held firm, displaying no signs of fatigue or impending failure. This wasn't just a successful test, it was a revelation. It proved, unequivocally, that the sacred dogma of precision machining, while undeniably valid for certain applications, was not the only path to reliability. Overwhelming and unprecedented demands of total war. Garand's bolt was not merely an incremental improvement. It was a paradigm shift. It showed that good enough, when engineered with ingenuity, a deep understanding of material science, and a willingness to challenge established norms, could unlock staggering efficiencies, dramatically reducing the resources consumed by vital production. The raw, desperate need for speed, for volume, had finally found its answer, forged in fire and validated by the unforgiving test of lead. The bottleneck that had threatened to choke America's war machine was not just relieved, it was obliterated, and the ripple effect of this quiet revolution would be felt across every theater of the war, saving countless lives and fundamentally altering the trajectory of American wartime production. The successful, undeniable test of John Garand's welded M1919 bolt sparked an immediate and unprecedented industrial revolution within the American war effort. The War Production Board, which had been agonizing over the chronic M1919 machine gun bottleneck, seized upon the idea with desperate enthusiasm. The news, passed up the chain of command, was met with a collective sigh of relief and a flurry of executive orders. Directives were immediately issued to retool factories across the nation and to retrain hundreds of thousands of workers. The change was implemented at lightning speed, a testament to the urgency and adaptability of wartime production. This wasn't merely adapting, it was an overnight transformation of a fundamental manufacturing process. The traditional 27 man-hours required for each meticulously milled bolt plummeted. The new process, involving the high-speed stamping of several simpler, less complex components, followed by their precise welding, drastically reduced the production time. In some conservative estimates, the time saved per bolt was as much as 80–90%. This wasn't just an incremental improvement, a minor tweak to the assembly line. It was a quantum leap in efficiency, fundamentally altering the economics and logistics of machine gun production. Factories that had struggled desperately to keep up with the insatiable demand suddenly found their output soaring. Production quotas that had seemed impossible to meet were now not only achievable, but often surpassed. Skilled machinists, a precious and limited resource who were desperately needed for other high-precision tasks, such as the intricate components of aircraft engines, the massive breech blocks of artillery pieces, or the complex gearing of tank transmissions, were freed up from the monotonous, time-consuming task of bolt production. Their expertise could now be redirected to where it was most critically needed, amplifying the nation's overall productive capacity. Less skilled workers, including the millions of women entering the workforce, many for the first time, could be quickly and efficiently trained in the relatively simpler welding and assembly techniques required for the new bolt. The bottleneck that had threatened to choke America's war machine was not just relieved, it was utterly obliterated, replaced by a torrent of vital weaponry. The impact was immense, almost incalculable. Millions upon millions of M1919 machine gun bolts, once a scarce and precious commodity, now poured off the assembly lines, fulfilling the desperate demands from the front lines. This meant more machine guns for every infantry platoon, enhancing their defensive and offensive capabilities. It meant more defensive armament for bombers, giving the brave air crews a better chance against swarms of enemy fighters. And it meant more firepower for tanks, armored vehicles, and even naval vessels, ensuring that American forces were always equipped to meet the enemy. The quantitative effect was staggering and unprecedented. By the end of the war, it was estimated that this single innovation in manufacturing the welded M1919 bolt had saved over 50 million man-hours of skilled labor. That wasn't just an abstract number. It was the tangible equivalent of freeing up tens of thousands of highly skilled workers for many months, allowing them to produce other vital war materials that were equally critical to the Allied victory. The success of the welded bolt proved, beyond any lingering doubt, that in a total war, battlefield pragmatism and industrial manufacturing innovation were inextricably linked. It showed that sometimes the rejected idea, the unconventional approach, born of necessity and insight, was precisely what was needed to overcome seemingly insurmountable obstacles. John Garand's quiet persistence had not just proven a point, it had fundamentally altered the trajectory of American wartime production, delivering a critical advantage at a crucial moment in history. The resounding success of the welded M1919 bolt was not an isolated incident. It resonated far beyond the confines of Springfield Armory and the immediate crisis of machine gun production. It became a powerful, undeniable case study, demonstrating the viability and immense benefits of fabrication by welding for critical components, where precision was important but not absolute, where strength and volume were paramount. This innovative principle, once dismissed as heresy, quickly extended its influence across the vast landscape of American wartime industry. Engineers and manufacturers across the country, now thoroughly emboldened by Garand's radical success, began to meticulously re-evaluate other parts that were bottlenecks in their own production lines or that consumed excessive amounts of precious machine time and skilled labor. Complex gun components, traditionally carved from solid blocks of expensive, high-grade steel through laborious machining, were redesigned. Instead of starting with a single, massive billet, they were broken down into assemblies of simpler stampings or forgings, produced rapidly by high-speed presses. These basic, easily mass-produced pieces were then brought together and expertly joined by welding. This transformative approach was applied to a wide array of vital war materials, from the receivers of submachine guns, which previously required significant milling, to critical components for anti-aircraft guns and even structural elements within military vehicles. The ethos of good enough for combat, a pragmatic balance between absolute precision and battlefield reliability, began to permeate the entire production process, prioritizing speed, volume, and robust functionality without compromising essential safety or performance. This fundamental shift represented a profound change in engineering philosophy, one that deliberately moved away from pure artisanal precision, often rooted in 19th-century craft traditions, towards a more industrialized, modular, and adaptable approach. It paved the way for vastly faster design cycles, easier material acquisition, and a more resilient, flexible supply chain. When a critical component could be manufactured from readily available steel sheets, stamped into shape, and joined by widely trained welders, it became less dependent on specialized, slow-to-produce milling machines and highly specific, often scarce, grades of steel. This democratized the manufacturing process, making it less vulnerable to bottlenecks in skilled labor or specialized equipment. The welded bolt's influence also reached beyond small arms, though its most direct applications remained there. While not directly applicable to every complex, high-tolerance component, such as the internal parts of aircraft engines, where absolute precision was non-negotiable, the mindset it fostered had a broader, pervasive impact. It encouraged engineers and designers across all industries involved in the war effort to think creatively about how to simplify designs, how to reduce machining time, and how to leverage new, faster production techniques like automated welding and advanced stamping. This relentless, pragmatic push for manufacturing agility and efficiency became a hallmark of American wartime industry, allowing it to adapt and overcome challenges that would have paralyzed more rigid, traditionally bound systems. The Mad Welder's trick, initially dismissed as an act of desperation, had become a foundational principle for wartime production, saving untold amounts of time, money, and most importantly, enabling the rapid delivery of the weapons that would arm the fighting men and women of the Allied forces on every front, tipping the scales decisively towards victory. To truly, profoundly appreciate the monumental impact of the welded M1919 bolt, one must attempt to visualize the staggering scale of the man-hours it liberated. 50 million man-hours. That is a number so vast, so astronomical, that it strains the very limits of human comprehension. It is a statistic that stretches far beyond individual experience and into the realm of national, even global, effort. This wasn't merely a saving. It was the equivalent of freeing an entire army of skilled labor. Imagine a single machinist, a highly skilled, irreplaceable craftsman, spending 27 grueling hours shaping a single bolt from a block of steel, each movement precise, each cut measured. Now, multiply that by the millions of bolts needed for the insatiable maw of the war effort. The original production method, rigidly adhered to before Garand's innovation, would have consumed the equivalent of over 1.35 billion hours of human labor, a staggering, almost impossible sum for a nation already stretched to its limits. By reducing that time so drastically, by implementing a process that took only a fraction of the original hours, the welded bolt effectively created hundreds of millions of man-hours that could then be immediately redirected. What did those precious, saved man-hours build? They built more Liberty ships, those utilitarian titans of the sea, ferrying vital supplies, troops, and equipment across U-boat-infested waters to every theater of conflict. They built more M4 Sherman tanks, breaking through the ancient hedgerows of Normandy, fighting across the muddy plains of Europe, and pushing through the jungles of the Pacific. They built more P-51 Mustangs, those iconic Cadillacs of the sky, escorting bombers deep into German airspace, dominating the Luftwaffe. They built more B-29 superfortresses, flying above the Pacific towards Japan, delivering the decisive blows of the air war. These weren't just abstract numbers on a ledger. They were tangible weapons, vital equipment, and essential supplies delivered to the front lines faster, in vastly greater quantities, and often at a significantly lower cost. Each saved hour meant a faster flow of resources to the fighting fronts, a quicker response to battlefield demands, and, crucially, a measurable shortening of the war itself. Every single day, the war continued meant more lives lost, more cities destroyed, more suffering endured across the globe. By accelerating the production of such a critical component, John Garand's innovation directly contributed to ending the brutal conflict sooner, saving countless lives and hastening the arrival of peace. The hidden, almost invisible, benefit was also in the immense flexibility and resilience it afforded the entire industrial complex. When a critical component became easier and faster to make, the entire chain of production became more robust, less fragile. It became less susceptible to labor shortages, less dependent on specialized, hard-to-acquire machinery, and far more capable of rapidly scaling up production to meet unforeseen demands or adapt to changing battlefield requirements. This newfound resilience was absolutely vital in a war characterized by constant technological innovation and ever-changing tactical needs. The rejected gun didn't just save time, it saved the fundamental flow of America's industrial might, proving that even a seemingly small change in manufacturing philosophy could have cascading, war-winning consequences that reshaped the entire trajectory of the global conflict. The story of the welded M1919 bolt is more than just an inspiring anecdote of wartime ingenuity. It is a profound and enduring lesson in the human tendency to cling stubbornly to orthodoxy even in the face of desperate and undeniable need. The initial, widespread rejection of John Garand's radical idea was a classic, almost textbook, example of this pervasive human trait. Experts, highly skilled and supremely knowledgeable in their respective fields, engineers, metallurgists, ordnance officers, found it almost impossible to believe that a fundamental manufacturing principle, one they had been taught from their earliest days in industry, that critical, high-stress parts required precision. Milling from a single, solid block of metal could be challenged, let alone demonstrably improved upon, by a technique they considered inherently inferior and crude. This resistance was not born of malice or ill will. It was, at its core, deeply human. It stemmed from a powerful, deeply seated trust in established methods, from a professional aversion to risk, and from the profound professional pride associated with high-precision craftsmanship. To accept Garand's welded bolt was, for many, to admit that their meticulously crafted, time-consuming, and highly specialized process was, in that specific context, profoundly inefficient. It required a painful willingness to question deeply held beliefs, to challenge the very foundations of their professional identity, and to embrace a pragmatic, results-oriented approach over a rigid, almost dogmatic adherence to tradition. The very notion of good enough for a critical firearm component felt like a betrayal of their standards. It took the undeniable, irrefutable evidence of repeated, successful tests under simulated combat conditions to finally break through this deeply entrenched resistance. It took the escalating, desperate demands of the war itself, the constant reports of equipment shortages from the front lines, to force a profound re-evaluation of what truly constituted quality and reliability in a time of total war. John Garand, the quiet, persistent, mad welder, wasn't just inventing a new, more efficient way to make a bolt. He was, in a very real sense, challenging an entire industrial philosophy. He was proving that innovation could come from anywhere, that the expert on the factory floor, grappling directly with the immediate, visceral problem, could often see solutions that escaped those far removed from the dirt and grime of immediate production pressures. The enduring legacy of the welded bolt is not just its quantifiable impact on wartime production, but its profound philosophical impact on American industry. It became a powerful, lasting symbol of the wartime drive to innovate, to adapt, and to question everything in the relentless pursuit of victory. It taught a generation of engineers and manufacturers that sometimes breaking every rule, rejecting the pursuit of theoretical perfection for the sake of good enough and fast enough, was not a compromise, but the greatest act of ingenuity of all. It was a testament to the power of one individual's conviction to shatter industrial dogma, to redefine what was possible, and to pave the way for a more efficient, adaptable, and ultimately victorious future. A future where pragmatism would forever stand shoulder to shoulder with precision. The M1919 machine gun, now famously equipped with its once rejected welded bolt, served reliably and effectively throughout the entirety of World War II, seeing relentless action in every theater of the global conflict. It continued to serve with distinction in subsequent conflicts, including the Korean War and Vietnam, a testament not only to its robust original design, but equally to the effective manufacturing techniques, including John Garand's pivotal innovation that ensured its massive availability and unwavering reliability. The specific, desperate need for which the welded bolt was designed eventually faded as new, more advanced weapon systems were developed and as manufacturing techniques continued their relentless evolution. But the profound lessons learned, the fundamental principles established by John Garand's crazy idea, left an indelible and lasting imprint on American industry and military procurement that continues to resonate to this day. The willingness to embrace fabrication by welding for structural and even some critical components, when it offered significant advantages in speed, cost, and material efficiency without compromising essential safety or performance, became a permanent and accepted part of the manufacturing landscape. It directly influenced the design and production of subsequent firearms, a wide array of vehicle components, and countless other wartime and post-war products. The revolutionary idea that simpler, more efficient manufacturing methods could yield robust and reliable results, once considered an engineering heresy, became a cornerstone of modern industrial production, permanently altering the way things were made. The story of the mad welder and his rejected gun is therefore more than just a historical anecdote. It is a powerful and timeless reminder that true innovation often arises from unconventional thinking, from the fertile ground of necessity, and from a pragmatic response to urgent, seemingly insurmountable problems. It speaks to the unsung heroes of the home front, the countless individuals whose quiet ingenuity, tireless hard work, and unshakable belief, far from the dramatic battlefields, directly and decisively contributed to victory. John Garand's bolt, a small, unassuming piece of steel, became an enduring symbol of America's unparalleled industrial might and its extraordinary capacity for radical adaptation and innovation under the immense pressure of global conflict. It wasn't a glamorous invention.